Hello, my name is Nuray Kayakol. I will talk about Eulerian and Lagrangian flow descriptions. Here is the outline of my seminar. First, I will introduce myself. My career path might inspire fresh safety engineers. And then I will describe Eulerian and Lagrangian approaches for the modeling of fluid motion. Then, after giving some examples, I will compare those methods. Then I will describe types of time derivatives. Finally, I will show implementation of these derivative terms on a CFD software. I'm a CFD engineer and worked for glass, energy, and automotive industries. I have coding, open source code development. So I have both academic and industrial experiences. I worked as a CFD scientist for code development, and then in industrial firms, I worked as a CFD engineer for industrial CFD applications. This career path might give you some suggestions how to choose workplaces or industrial sectors. So it depends on your choice, because CFD engineer can work any industrial sector. This depends on how you gain information about CFD theory, so you can solve complex problems. Let's start a lecture. I will talk about two methods or approaches for the modeling of fluid motions. These are namely Eulerian and Lagrangian approaches. First of all, let me give them their proper description. Eulerian approach describes the variation of fluid flow at all fixed points in space as a function of time. So when we read this definition, you will understand, first of all, this is ideal for flow simulation. This description mentions fixed position in space. That means there will be some flow domain discretization. And then it talks about the function of time. That means variable will be not only the position in space, but also function of time. So this tells us simulation can be transient or steady state. Basically, what we do in CFD simulations, we apply Eulerian methodology. How about the Lagrangian approach? Let me read the definition. Lagrangian approach describes fluid flow by tracking the individual particles along its trajectory. So this description mentions about not only the fluid flow, but the particles. And it is ideal for particle motion. We need to understand both methodologies, because in fluid flow we have also particles. Let's learn Eulerian approach in details. In previous slide, you learned that Eulerian approach mainly deals with position in space as a function of time. This tells us, first of all, variables, this is denoted by phi, will be function of x, y, z, that is the position in space, and t stands for time. if you talk about location of variable, that means flow domain is discretized. This tells us mesh. So how do you discretize the flow domain? So first of all, you have a geometry. You create mesh. That means you will have some kind of control volumes, and you will apply either a finite volume or finite element method. Most important feature of Eulerian approach, mesh does not depend on material. So if you think about how you create mesh for your geometry, you're never interested whether material is gas or liquid. You just create small control volumes or elements without thinking the material. So because of this, Eulerian approach is ideal for flow simulations. How about the Lagrangian approach? In Lagrangian approach, we are interested in particle tracking. So variable is defined as a function of time. So if I go back to the first previous slide, you will see phi as a function of x, y, z, and t in Eulerian approach. How about the Lagrangian approach? It becomes as a function of time, and mesh is based on material, and those kind of approach rarely used for flow simulation. So this actually this methodology is for particle motion. So if I summarize Eulerian and Lagrangian approach, in Eulerian approach, we discretize flow domain. We use mesh-based methods, and we express the values of variables, for example, temperature, pressure, or whatever, at fixed position as a function of time. So this is actually what we do for flow simulations. In Lagrangian approaches, variables will be described as a function of time, and ideal for particle motion. This is, although we have particles in fluid flow, Lagrangian approach actually mesh-based Lagrangian methods is rarely used, because you need to change the mesh according to particle position. So we do different. So I will describe in a minute. To understand Eulerian approach, we need to understand what is the meaning of physical meaning of control volume. On this picture, we have an observer, this green guy, and then observes a small control volume. So in this control volume, flow go through fluid flow. What does it mean? In CFD simulation, first we define our geometry, we create a CAD model, and then we apply meshing tools to have some control volumes. Here is a kind of box. So if you divide the geometry into small control volumes, that means you fix the position of control volume. You already have many control volumes, so each point actually, or around, it is placed in a control volume, so flow enter in different coordinates. Flow moves through this control volume. Why do we do this? Because we want to express fluid flow variables like velocity, density, pressure, or temperature as a function of time. So we should allow flow moves through the control volume. This is how it is done in Eulerian approach. How about the Lagrangian approach? The position of observer is different than the Eulerian approach, because in Lagrangian approach, particle is tracked. That means observer is moves with the control volume. This arrow shows a path line for flow trajectory, and at different time step, position of control volume is changing. This is how we understand Lagrangian approach. To understand you better, consider flow in a pipe. Suppose that we define an inlet. Right hand side you might think as an inlet, left hand side as an outlet. Flow will go through this pipe. Suppose that this is a laminar pipe flow. These arrows with different colors will tell you pipe flow pattern, parabolic flow pattern. So it is maximum at the center, and then it is decreasing as it's getting close to the wall. Why? Because velocity is zero at the surface. That's why we have such a parabolic flow pattern. So we can easily simulate this in Eulerian framework. Suppose that we have a particle injection. Then we can use Lagrangian approach. This red dot shows a particle, and then these arrows actually show flow pattern, so you can define how these particles are injected to the flow. So you have to define particle direction or velocity or position. Then you need to track these particles. Now I will give you 3 examples so that you can understand Eulerian and Lagrangian flow pattern. These examples will be traffic flow, and then multiphase modeling for cyclonic separator, and the third one, particle moving in a square duct. Let's talk about traffic flow. You see a highway, an observer is standing nearby. Then at a fixed position, observer reports number of cars. So observer can report number of vehicles for a specified time period. For example, 100 vehicles per hour. This will be an Eulerian perspective work. Of course, this will not be done by a person, and this is just an explanation or an example. In reality, sensors does this work, but This can be done by an observer. So this is an example. And the other way could be Lagrangian approach, actually most suitable one for this kind of application. Observer, you see, stand by the car, just imagine like this, and the blue line shows flow path of these cars, and GPS or cell phones can provide data for individual cars. If these information are collected, then traffic flow can be obtained or plotted. So this will be the Lagrangian approach. Observer will move with the object, but in Eulerian approach, observer will stand outside of the flow, traffic flow. This will be the daily life example. Let's talk about an industrial one, multiphase modeling for cyclonic flow. If you read CFD papers, if it is a single phase simulation, nobody will talk about Eulerian or Lagrangian approach. But if you read papers similar to this cyclonic separator simulation, author first of all should tell how gas and particles are treated. One of the options could be Eulerian approach. This means gas flow and particles are expressed using Eulerian approach. So it's a double. That's why it's repeated. The other option, particles can be tracked, but gas flow can be used as before using Eulerian approach. Then we call this Eulerian Lagrangian approach. So if you read those terms, if they are equal, Eulerian approach, that means both phases modeled using Eulerian approach. So you will never read Lagrangian approach, no. For gas flow or fluid flow, we basically use Eulerian approach. Maybe Lagrangian could be for particles. In this picture, you see cyclonic separator. There are some blades, and you see the air vectors moving through these blades because of the cyclonic flow. Particles, large particles will move around these blades, and the smaller one will move another one inside. You see there are two rows of blades. One is outside, the second is inside. So this will be for particle separation. Of course, you don't see particles because number of particles are very small compared to fluid particles. Actually, this is a dilute system. So this maybe later on I will give another lecture for cyclonic separator. So this is good enough to understand how we model gas and particle flows in such a system. The third one, suppose that we have a square duct and a particle is ejected. So let's talk about this graph In this picture, you see 10 times 7 elements or grids. If we count number of boxes or grids along horizontal direction, it will be 7, 1, 2, 3, 4, 5, 6, 7. So on the vertical one, we have 10 boxes or grids, so totally we have 70 elements. That means this box is meshed with a structural grid. The particles moves from 1 to 6. You see this light blue arrow will show Lagrangian path or line. So depending on your time section, or so you will catch the particles at certain positions, so it's changing from 1 to 6. Then particle reaches to the outlet, and you see the number 6 on the top of the corner, close to the corner on the right. So this is the particle path, and the control volumes are Eulerian control volumes. So I put some numbers 1, 2, 3, 4 to show you the corners of the control volume. As you see, the number 4 not at the corner of the control volume, but hits somewhere. Because if you solve such a system, gas phase can be treated as continuous phase, and Navier-Stokes equation can be solved for particles, and can be treated as a discrete phase or dilute phase. So all you need to do is apply Newton's law of motion and calculate some forces acting on the particles, like drag, gravitational, and buoyancy forces, whatever specific this problem. This is how gas and particles are treated in Eulerian Lagrangian approach. So red points are the Eulerian points, and blue ones is the Lagrangian points. Now let's talk about how these particles are ejected. So in the program, you have to choose location of particle, and then give some, you can define some velocity, and then program will calculate how this particle moves from 1 to 2 or 2 to 3. So this is how path lines of a particle can be used for Lagrangian calculations. And then because I'm just giving more information so that you can see Eulerian control volumes. In this example, 10 to 7, that is 70 grids we have, and each control volume gas flow is calculated. Okay, this is another summary how we compare Eulerian and Lagrangian approach in CFD simulations. We use Eulerian approach. We just define an inlet and outlet, fluid moves between those locations. Then we use Eulerian description. If we have particles, we just follow the Lagrangian approach for particle tracking. So let's continue to compare. So on the left-hand side, you see some parameters and how we deal those parameters with the Eulerian approach. Location of observer is outside of the control volume. Remember, I give you a traffic flow example. The observer was standing outside of the highway. Velocity of observer, stationary, because again, remember traffic flow example, observer was standing nearby highway. That means the position is fixed and it doesn't move. And variable is defined depending on position. You see, if it is 3D, it will be x, y, z, and then time. Location of the control volume, fixed in space, because when we mesh the geometry, you define the control volumes, or you define number of elements. That means you fix the control volumes. Can fluid pass through the control volume? The answer is yes. If no, how will you calculate, for example, temperature at certain XYZ position? So if you remember the control volume, we calculate, for example, temperature in the middle of the control volume, or velocity on the faces of control volume. On the Lagrangian one, in contrast to Eulerian approach, location of the observer on the control volume and the velocity observer is not stationary but the same as fluid flow velocity. Then variable values of variable is reported or calculated as a function of time. Location of control volume. How we will answer this question? If the velocity of observer moves with the fluid velocity, and then observer on the control volume, that means location of control volume moving along the path line with the velocity equal to the local flow velocity. This is obvious because both observer and control volume is not fixed, they move. Can fluid pass through the control volume? No. This is if it is yes, it will be a Eulerian approach. On this slide, you will see previous slides in one table to compare Eulerian and a Lagrangian approach. So if I repeat once more, for fluid flow calculations, we use Eulerian approach, and it's a mesh-based methodology. We discretize flow domain into many control volumes, and we express values of variables like temperature, velocity, or other quantities as a function of space coordinates like x, y, z in 3D, and then time. In the Lagrangian approach, we use we apply this methodology for particle tracking. Observer or control volume moves along the path with a velocity equal to the local flow velocity. Why? Because inertia is coming from the fluid flow velocity. This will be the comparison of Eulerian and Lagrangian frameworks. So after learning these things, let's start equations, how we will drive equations. So in order to do this, we need to learn three types of time derivatives: partial derivative, total derivative, and substantial time derivative. Maybe you are familiar d over dt, that is the differential term. In differential equations, the derivative is expressed d over dt. But partial derivative, we use a different operator. This letter is partial operator. The other one is the substantial derivative, that is the big d over dt. Now we will learn these terms in detail. Partial derivative. Partial derivative actually is when the observer position is fixed. Do you remember in Eulerian approach, position of observer was fixed, and you see del phi over del t. Phi is the sense for variable. This could be a temperature, for example, del phi over del t. So you see outside of the bracket you will see x, y, z. That means these terms are constant. Del phi over del t is a partial derivative of variable phi with respect to constant x, y, and z. So this is actually a kind of Eulerian approach. By the way, in short, I say del phi over del t. This is short way of reading the equations. Yeah, instead of del phi over del t, you can read partial derivative of variable blah blah. So this is also del phi over del t is also called time rate of change. So you will see later on how partial time derivative can be expressed. If I give an example, if phi is rho, and so with some terms you can obtain conservation of mass. So partial time derivative, also called transient term of a transport equation. You see partial derivative of phi with respect to time given in bracket, and then there are some other terms: convective term, diffusion term, and generation term. So this slide tells you where do we use partial time derivative in a transport equation. Below this equation, you see del phi over del x, del phi over del y, or del phi over del z. These are not partial time derivatives. These are partial derivatives of phi with respect to space coordinates. So you need to see the difference between partial time derivatives and the other partial derivatives with respect to space coordinates. So where do we use these terms? In the convective term. This will be subject of another lecture. The other one is the total derivative. This total derivative will give you time rate of change of variable phi. So d over dt is expressed. So just I'm reading the terms. The first one is the partial derivative of variable phi with respect to time. This is what we learned previously. The other one is del phi over del x, del phi over del y, or del phi over del z, variation of variable phi in x, y, z directions. How about the terms dx over dt, dy over dt, or dz over dt? These are the velocities of observer. That means observer is a meaning. If you consider time, total time derivative, observer is moving. What was the previous definition of partial derivative? Observer position is fixed. But when we write total time derivative, observer is moving. So there is another time derivative. It's substantial time derivative. Big D over dt. In this equation, the first term is the partial derivative of phi with respect to time, that is the transient term, and then there are terms Vx, Vy, Vz. These are the velocities of observer. That means observer is moving with the fluid flow. If we compare this total time derivative, the velocities observer was changing. It has nothing to do with the fluid flow velocity, but in substantial derivative, observer is moving with the fluid flow. So d over dt is expressed in vector form, del phi over del t plus v dot, this is dot operator, del phi. This is also, this is a quick way of reading the equation. Actually, I also use del for the nabla operator. So don't confuse del phi over del t, but this is commonly used. But nabla operator also used as del operator. Del operator is the actually summation of partial derivative of space coordinates x, y, and z. So if you compare this nabla equation with the total substantial time derivative equation, you see phi is dot product of phi will give del phi over del x, del phi over del y, del phi over del z. Then velocity in vector form is, for example, v sub x. Vx is velocity in x direction, velocity in y direction, or velocity in z direction there. This is a typical dot product of velocity with the del operator of phi. Let's see substantial derivative in detail. Usually d over dt is defined as Lagrangian derivative. Why is that? Because if we go back to this equation, because observer is moving with the fluid flow, that's why we call it Lagrangian. The other terms, Eulerian derivative, del phi over del t, or this v dot nabla or v dot del operator. Some people call v dot del as a convective term because you multiply partial derivative of variable with respect to coordinates with the fluid flow velocity. That's why it's called convective, because this velocity term. So in this equation, substantial derivative term has both Lagrangian term and Eulerian term. Left hand side of the equation is Lagrangian because in the here on the right hand side we have a velocity term that is observer is moving with the fluid velocity. Right hand side is called Eulerian derivative because del phi over del t is Eulerian way of expressing the variable, because position is fixed. Only a transient term is defined because it's a time partial derivative. Now, we learned Eulerian approach, we learned types of time derivatives and how this information will be useful to understand open form way of writing the transport equation. Okay, phi is the our variable. It could be any variable. It could be velocity, temperature, whatever. And transport equation, or you can also call Navier-Stokes equation. It has four terms. On the left-hand side, we have unsteady term, and then convective term. Unsteady term, remember, it was Eulerian approach we have, and then convective term. If you add these two terms, you will have substantial derivative of phi. On the right hand side, there's a diffusion term and then source term. In open form, unsteady term is expressed as d dt, del over del t. That's the short way of saying unsteady term. Div is for convection term. Div actually divergence or coming from the nabla operator. And the third one is it's called Laplacian because the second derivatives of phi, and the right hand side is the constant terms or terms multiplied with the phi variable. On the left hand side you will see derivative terms. On the right hand side as scalar values. S stands for source. So if we read these terms, that means finite volume method, d dt phi. So at least you can follow these. In this lecture, I gave this example. I'm not supposed to teach how to coding in open form, just to understand these terms, why it is coming from, why it is explained in that form. So at least you will understand which one is Eulerian, which one is Lagrangian term, or how substantial derivatives are expressed in open source code. So this is the end of my lecture. I hope you will find more informative. If you have questions, of course you can write it to me. Thank you for your time.